Hello, welcome students. I am Rekha Thorat, Associate Professor. Today I am going to discuss on the topic sequences of paper 7 real analysis 2. Let us consider theorem 1. Statement of this theorem is if sequence Sn going from 1 to infinity is sequence of non-negative real numbers and if limit of Sn as n tends to infinity equal to L, then L is greater than or equal to 0. That means here statement of this theorem is sequence of non-negative real numbers, that means positive numbers, and limit of this sequence is L, and we have to prove that L is greater than or equal to 0. Let us consider the proof of this theorem. We have given that sequence Sn and going from 1 to infinity is sequence of non-negative real numbers and limit of Sn as n tends to infinity equal to L. To prove that L is greater than or equal to 0, we prove the theorem using indirect proof. That means we assume the contrary. That is, we have to prove that L is greater than or equal to 0. Contrary, we have to assume the contrary. So that we have assumed that L is less than 0. Then for epsilon equal to minus L by 2, that means by definition of limit, given epsilon greater than 0, there exists some positive number like that. Then for epsilon equal to minus L by 2, there exists m belongs to I such that modulus of Sn minus L is less than minus L by 2 or n is greater than or equal to m. In particular, modulus of Sn minus L is less than minus L by 2. This implies L by 2 is less than modulus of Sm minus L is less than minus L by 2. Here modulus of Sn minus L is less than minus L by 2 for n greater than or equal to m. In particular that means for n equal to m, we have Sm minus L is less than minus L by 2, and this implies L by 2 is less than modulus of Sm minus L is less than minus L by 2. This implies Sm minus L is less than minus L by 2. Taking left half, taking right half. Sm minus L is less than minus L by 2. This implies Sm is less than minus L by 2 plus L. That means Sm is less than L by 2. This implies all Sm are negative. That means L is less than 0 and Sm is less than L by 2. This implies all Sm are negative. But by hypothesis Sm, we have given that sequence is of non-negative real numbers, so that Sm is greater than or equal to 0. This is contradiction to our supposition that L is less than 0. That means we have assumed that Sm is hypothesis. That means in the statement of this theorem, we have given that sequence is of non-negative real numbers, so that Sm is greater than or equal to 0. So that Sm is less than L by 2, that is all Sm are negative. This is contradiction to our supposition, that is L is less than 0. So this proves our theorem, that is L is greater than or equal to 0. Now we consider the next theorem. Statement of this theorem is if the sequence of real numbers Sn n going from 1 to infinity is convergent to L, then sequence Sn n going from 1 to infinity cannot also converges to the limit distinct from L. Or this statement can be written in the form as if limit of Sn as n tends to infinity equal to L and limit of Sn as n tends to infinity equal to M, then we have to prove that L is equal to M. That is, limit of sequence is unique. In this theorem, we have to prove that limit of sequence is unique. Let us consider the proof of this theorem. Let sequence Sn be a convergent sequence of real numbers. And let limit of Sn as n tends to infinity equal to L and limit of Sn as n tends to infinity equal to M. It means sequence Sn has two limits, L and M. We have to prove that L is equal to M. That is, limit of sequence is unique. That means we have to prove that L is equal to M. To prove that L is equal to M, we assume the contrary. That means we assume that L is not equal to M. This implies modulus of M minus L is greater than 0. Since limit of Sn as n tends to infinity equal to L, that means limit of sequence is L, by definition of limit there exists n1 belongs to I such that modulus of Sn minus L is less than epsilon when n is greater than or equal to n1. Also, we have given that limit of Sn as n tends to infinity equal to M. So, by definition of limit, there exists n2 belongs to I such that modulus of Sn minus M is less than epsilon for n is greater than or equal to n2. Let n equal to maximum of this n1 and n2. That is, n is greater than or equal to n1, n is greater than or equal to n2. Now consider modulus of M minus L equal to, this can be written as modulus of M minus L equal to modulus of Sn in bracket Sn minus L bracket complete minus in second bracket Sn minus M bracket complete and take modulus. Then by definition of some properties of modulus, modulus of M minus L is less than or equal to modulus of Sn minus L plus modulus of Sn minus M. Hence, modulus of M minus L is less than epsilon plus epsilon. Since modulus of Sn minus L is less than epsilon, modulus of Sn minus M is less than epsilon. So that we get modulus of M minus L is less than epsilon plus epsilon. That is, modulus of M minus L is less than 2 epsilon. Now we choose epsilon equal to modulus of M minus L upon 2. Hence, modulus of M minus L is less than 2 into modulus of M minus L upon 2. 2 cancels, so that we get modulus of M minus L is less than modulus of M minus L. And this is contradiction, since this is not the property, any number not less than itself. So that modulus of M minus L is not less than modulus of M minus L. That means we get here contradiction. so that our assumption, that is L is not equal to M, is wrong. Hence L is equal to M. That means limit of any sequence is unique. Thus we have proved the theorem. That means limit of sequence is unique. Hence if there are two limits of any sequence, then these two limits must be equal. That is L is equal to M. Now we consider some theorems. That means they which are without proof. There are only statements of this theorem. Theorem 3 is without proof. Statement of this theorem is if the sequence of real numbers, sequence Sn and going from 1 to infinity, is convergent to L, then any subsequence of this sequence Sn and going from 1 to infinity is also convergent. That means if subsequence of convergent sequence is convergent. Here this theorem is without proof. Another theorem is theorem 4, which is also without proof. Statement of this theorem is all subsequences of convergent sequence of real numbers converges to the same limit. All subsequences of convergent sequence of real numbers converges to the same limit. That means if any sequence Sn converges to L, then subsequences of this sequence Sn also converges to the same limit L. That means subsequences of convergent sequence of real numbers converges to the same limit. This theorem is also for without proof. That means without proof there are two theorems, theorem 3 and theorem 4. Theorem 3 is if sequence of real numbers converges to L, then any subsequence of this sequence also converges to L. And theorem 4 is all subsequence of convergent sequence of real numbers converges to the same limit. Now we will consider one definition of bounded sequence. Definition of bounded sequence. Definition is a sequence Sn n going from 1 to infinity of real numbers is called bounded above if there exists a real number m such that Sn is less than or equal to m for all n. That means sequence Sn is bounded if Sn is less than or equal to m for all n. A sequence Sn n going from 1 to infinity of real numbers is called bounded below. That means this definition is for bounded above. That means sequence Sn is bounded above if Sn is less than or equal to m. And now consider definition of bounded below sequence. A sequence Sn n going from 1 to infinity of real numbers is called bounded below if there exists a real number n such that Sn is greater than or equal to n for all n. That means bounded below sequence means Sn is greater than or equal to n for all n. Thus, sequence Sn n going from 1 to infinity is bounded if there exists m belongs to R such that modulus of Sn is less than or equal to m for all n belongs to I. In this definition, we have considered bounded above and bounded below, and finally bounded sequence. That means sequence Sn and going from 1 to infinity is bounded if it is bounded below and bounded above. That means sequence Sn and going from 1 to infinity is bounded if there exists m belongs to R such that modulus of Sm is less than or equal to m for n belongs to I. Thank you.